Hello everybody, welcome to the first lab of Engineering 3390, Signal Processing. In this lab I'm going to teach you how to use the signal processing board. I'm going to teach you how to connect it to the signal generator. I'm going to teach you how to connect it to the oscilloscope so we can see what's going on. And I'm going to teach you how to use the Code Composer Studio software that we use to program the board. First, let me introduce you to the equipment that we're going to be using. You can see here in front of you on the screen is the signal generator where I've got the camera focused right now. That is currently set to put out 20 kilohertz, which you can see on the display as well. And I have it connected to nothing right now, just a blank cable. So what I'm going to do is I'm going to connect it to this board here. And this is a small TI signal processing board. It's a USB stick. We connect it to the computer, we put the program on it, we connect the audio to these audio jacks here on the side, and that will connect up to the signal generator and to the oscilloscope. So let me plug that into the USB cable here now. I've got that plugged in now. Next up, we need to connect our mixer board, and that's this board here, this purple one. There are also some green ones you might have seen floating around as well. These purple boards have input and output for audio and allow you to connect the audio through these 3.5 millimeter jacks and also through these B and C connectors. So we can connect up all the different pieces that we need in order to make this lab work. I'll connect our audio input here to the jack labeled stereo in on the signal processing board, and then I'll connect the stereo out jack here to the one labeled HP out. And now I've got that board connected to the mixer, but I still need to get the signal into it. And we do that with this cable right here. This is connected to the input part of our board here. Screw it on tight, and then we'll connect up the oscilloscope as well. And we do that with these other two cables here. This one here is the right channel, so we'll put that as our output so we can see what's coming out of the board. And this one here is our left channel, or our channel 1, and we'll put that into our input. So we have channel 1 connected to input, channel 2 connected to output. Now here is the oscilloscope, and on the oscilloscope you can see that the sine wave is currently visible. We're going to press auto set here just to see what comes up and if we can get a clearer picture of that waveform. And we can get a fairly clear picture of the yellow waveform. That's channel 1, the input, and the output is telling us nothing more than noise. If we zoom in with the vertical scale on the knob here, we can see it's a lot of noise. If we hit single, we can see one particular type or one particular snapshot of the noise there. Turn that menu off. Or we can let it run. And we can see have our input appear, sine wave. Looking at the bottom of the screen here, you can see that the peak-to-peak voltage on that sine wave is 1.36 volts. The frequency is just around 20 kilohertz, wandering up between 19.9 and 20.03 or so. Meanwhile, on channel 2, we can see that the peak-to-peak is a lot smaller, and really we're just seeing a lot of electrical noise there because nothing's coming out of our signal processing board yet. Next, we'll take a look at the Code Composer Studio software, which you can see on your screen now. As you can see, the code for this board, and for most embedded systems you'll come across as an engineer, is written in C, which I'm sure most of you will remember from your programming courses that you've taken in the past. So at the top of this file, we have our description of the file, author, file name, etc., comments mostly. The real meat of it starts down here on line 54. The pound include that you see there is probably familiar to you from your C experience. That's how we get access to built-in functions that allow the computer to communicate properly with the board. Standard input-output is for keyboard and display, but the other ones here you'll see are for actually communicating with the board itself. Next up, we have some constants that we've defined. Global variables for our left input, our right input, our left output, and our right output. We've also defined a constant called samples per second. You'll see 48,000 as samples per second in lots of places. That's a very common number for audio. You'll learn why about that once you learn about the Nyquist sampling rate once you get further into this course. Finally, down here at line 75, we get to the main function. And this has several pieces of code that's really just for initializing the board. This one here called USB STK initialize, that initializes the board. We also initialize the PLL, that sets the frequency properly for the board to actually communicate and generate signals effectively. A couple other hardware initialization functions, some code that prints things to the output for us to follow along. And then what really matters for us is what's between this for loop, what's between these curly braces here. This for loop starts at I equals 0, runs up to samples per second times 600. So 48,000 samples, 600 seconds equals 10 minutes. And that will allow this to run for 10 minutes, constantly sampling at that sampling rate, and then executing this code that you see here. This is a very fast, tightly written loop in here where it simply reads from the signal processing input. It reads the left and right channels. It then maps the left input to the left output, and it maps the right input to the right output. Very simple processing here. It's literally just passing through the signal. Once it does that, it writes to the output the things that we've said, the left output and the right output. And then after that, it loops over and over again for 48,000 samples per second times 600 seconds. Okay, so let's start this program here. It's already initialized and ready to go, so I'll click the debug button to open up the debugger. We'll save the file, the main.c. We'll watch it as it builds here. It builds the target, the build finishes, and then it'll launch the actual debugger program. We will hit play, and we'll start the program. Let's go see what that looks like on the oscilloscope. And now you can see what the output looks like on the oscilloscope. If we look really closely at what we see on the screen here, we have our input is still visible, the yellow channel 1 at the top, and we also now have an output passing through a very similar signal on channel 2. If we take a single shot of that, we'll see that the output is significantly noisier than the input. That's a result of the processing in the signal processor. If you recall, we talked about how we're sampling at 48,000 hertz. That means at 48,000 times a second, the board takes a snapshot of what the signal looks like, and then after a set period of time, it takes a second snapshot. That's going to show up as imperfect representation of the final result. For this lab, we're going to change our signal from 20 kilohertz input. We're also going to show 10 kilohertz and 5 kilohertz. So let's go ahead and change our signal generator to 10 kilohertz now. We're going to change the coarse adjustment frequency, but first we'll set the fine adjustment to the middle, which will give us some room to play on either side. Turn the coarse adjustment frequency down, off from our 20K, we're down to 12. We'll get it as close to 10K as we can with the coarse adjustment, and then fix it with the fine. As we're doing this, watch what's happening on the oscilloscope. You can see the length of the wave is actually changing on the screen. That's showing that this is a much lower frequency input. This is a bit hard to see the way it is right here, so let's change our horizontal scale as well. If we turn this knob here, we can zoom back out one tick. It actually looks pretty similar to what we saw before. But if you notice down in the bottom of the screen, you'll see that the frequency on channel 1 is 10.02 kilohertz or so. Hit single to show one line. We still see that noise there on channel 2. Another thing that we see on this is the phase shift between the two signals. So this one, channel 1 here, is the input. It's being read by the processor. But the processor needs to take some time to actually do the processing on it. There's not much processing, but there is still a delay between those two signals. And you can see that delay on this output works out to a phase shift of what the oscilloscope reads as negative 40.05 degrees. But in reality, because the output has to come after the input, it's going backwards about a delay of 320 degrees. So now that we've seen it at 10K, we're going to show what this looks like at 5 kilohertz as well. For this one, we're going to need to change the range on our signal generator. And now it's jumped all the way down to 1,000. because we've changed from 100K range to the 10K range. Let's change the frequency up to something more like 5,000. And again, as I'm turning this knob here, we'll look at what's going on the oscilloscope to compare that as well. We'll make sure we get it around the 5K mark and then adjust the fine adjustment to bring it closer. And that's close enough. So again, we're seeing something very similar to what we saw already. We're seeing our input looking like our input and our output looking a lot like our input but noisier. Again, changing our horizontal scale, running it, showing a signal. We are still seeing that noise, but it's very difficult to see it when compared to the size of the signal. Now, if you look on the screen, you'll see we've changed our samples per second from 48,000 down to 24,000. Now let's see what happens to our signal when we do that. So now we're back here on our 20 kilohertz input, and we're running it at a 24,000 hertz or 24 kilohertz sampling rate. So let's take a look at our signal generator and our oscilloscope again. Our input still looks the way we expect it to, approximately 20 kilohertz, but our output, well, you can see what our output looks like there. Even if we go to single, we really can't see anything more than noise. Now let's go and change our signal generator back to 10 kilohertz and see what happens next. It's a bit too low. But watch that oscilloscope as I turn my signal generator down past the 12 kilohertz mark and then go further down. There we go. We're right at 10 kilohertz there. And we take a look at our oscilloscope, hit single, and we can see again we've got a fairly adequate representation of our wave. Even if we zoom out and look at a wider angle view of it, we still see we've got our 10 kilohertz in and our 10 kilohertz out. Let's do it one step further and then watch as our signal changes down to 5,000 hertz. Set that up here, get it pretty close. There's no need to be completely accurate. And again, we can see that we've got a fairly adequate representation of our signal there. And now we're going to change our samples per second once again, this time down to 8,000 hertz. So let's do that now. We'll stop our actual run here so we can recompile it. We'll save the 8,000 hertz that we've got in here, and I'll click debug again to start the program. And then we'll get to the breakpoint once it finishes building and click resume. And here we are back looking at our 20 kilohertz signal coming in, and again we see we have nothing of value coming out on that output. Let's see what it looks like for 10. Changing the frequency down to 10 really quickly here. And this time, 10 kilohertz also doesn't look like anything at all. So what do you think is going to happen if we do 5 kilohertz? Well, let's see. Even if we zoom out on the scale there, even if we pause it and show a single frame, we got nothing. Would you be surprised if I told you that I'd have to drop this all the way down below 4,000 hertz in order to start to see that sine wave coming through again? In the next part of the lab, we're going to see what happens when we do something called decimation. I have some code up here on the screen right now that accomplishes exactly that. Decimation, of course, if you did your pre-lab, you'll know is what happens if you were to downsample your input by setting half of the samples to 0. So I have a little piece of C code here that you might be familiar with called the modulo operator. And this modulo operator is actually checking for the remainder. Every time we run through this for loop, we increment this counter I by 1. If that I counter is odd, the remainder is going to be 1. If the I counter is even, the remainder is going to be 0. So this is saying, is the remainder 0? Is the I counter even? Then we will actually write our input through properly. But if it's odd, if it's not even, if the remainder is not 0, we're going to set our output to 0 instead. So we're going to run this code now. I'll stop our former run here. We will go back through debug. Might ask us to save. And then we'll play and we'll see what happens there. So let's go take a look. So now we're looking at our decimated signal at 20 kilohertz. And that is really something interesting that we're seeing there on that output, isn't it? It is still showing through the initial signal. The 20 kilohertz signal can be seen here, but if we look at it and try to see what's going on, there's a lot of other noises in there. There might be some low frequency noises in there. You can kind of see it if we cycle through these things. At sometimes the ones on the left are higher, sometimes the ones on the right are higher, and those peaks will change depending on exactly when I hit this single screenshot button. Now let's take a look at what happens when we've got 10 kilohertz up there. We'll just drop this back down once again and take a look at our signal. And that oscilloscope certainly looks interesting, doesn't it? Let's zoom in a little bit here, maybe take some single looks, change our scale, and you can see again the output wave there is very different from the input wave. It looks like there's definitely some low frequency noise going in there that's canceling out some of those peaks. Finally, let's take a look at what it does at the 5 kilohertz mark. Put this about in the middle there, a little lower than that maybe. And you can see that we've got some very interesting things going on that as well. So in this one, the noise is actually a high frequency noise. The output waveform is going back to 0 a lot of the time. And you think about what we told the processor to do, that's exactly what we'd expect. We're telling it every second sample to go to 0. In this case, we could actually physically see that going to 0 each time. You can still see the 5 kilohertz signal in there, but it's got a great deal of high frequency noise as well. Now we're going to change our decimation from every second input to 5 out of every 6 inputs. And we're going to see what happens then. And this is equivalent to a decimation down to 8,000 kilohertz, like we tested earlier with the sampling rate. And to do that, I will still pass through the left output to the left input, but at this time only every 6th time. Every other time it'll go to 0. And the reason this works is because now we're checking I against the remainder of dividing it by 6. Only when that's 0 every 6th sample are we going to let the input actually go through. Otherwise, we set the output to 0. And now we're looking at what happens when we do that 5 out of 6 decimation. Here at 20,000 hertz, 20 kilohertz, we'll change our horizontal scale again, and we'll get some snapshots of what's going on there. While you can sort of see that there's some semblance of a 20,000 hertz signal in there, it's really all just noise. Now let's take a look at what it looks like at 10,000 hertz. I'm still seeing a lot of noise there. We're a little bit low, but that should be fine. We can look at some of these freeze frames. I'm still really only seeing noise there. So we'll drop it down to 5,000 and see what happens. But of course, when we're losing that much of our signal, we really don't expect to see anything at all on the output. Now we're going to do our 0 order hold. Now instead of having our modulus of 6, we'll go back to our modulus of 2 to do a 24 kilohertz 0 order hold. Instead of setting our left output and our right output to 0, we're just going to store what we did before. If you're familiar with C, you'll understand why this works. So I'll try to explain it to you. I'm going to delete this else statement. And now what's going on here is we are only writing the output when we're on the even numbered samples. If we're not, these have the same value that they had on the previous loop. They're not changed at all, so we're just going to write the same output again. And that's the easiest way to do a 0 order hold. Here at 20,000 hertz, we're really seeing just straight up noise again. There's not much to see here on the oscilloscope. Even if we freeze frame it, we're not getting much at all. Kind of as we expected, I think, by now. So we'll change our oscilloscope here, and we'll change our signal generator as well and see what happens as we approach 10,000 hertz. That's close enough. Well, we can definitely see that we have something resembling our input there, though it's definitely really noisy. Let's take a look at that signal again, and we'll screenshot that. We're not seeing too much helpful there. We've got our input signal, we've got our output signal kind of matching that, but there's a lot of higher frequency noise going on in the meantime. And let's drop it down to 5 kilohertz just to see what happens. And here at 5 kilohertz, well, same story again. We've got a lot of noise, but we've still got a recognizable 5 kilohertz signal on that output. When we hit single, now we can maybe even get a little bit of an idea of what's going on. It's not perfect, but we can absolutely see that we have some parts where it seems to be staying flat before it jumps back to the next lower signal. And that's exactly what we expected to see, given that we're doing a zero order hold. And now finally, let's take a look at what this looks like when we do a zero order hold for 5 out of 6 samples. On a 20 kilohertz input here, we still see some semblance of a 20 kilohertz output hidden in that noise there. When we drop it down to 10 kilohertz, same story, there's nothing there. And finally 5 kilohertz, again, we're just not seeing anything there. As we drop it down lower, 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 there's nothing. So there you have it. Various downsampling methods for mimicking 24 and 8,000 hertz sampling rates, as well as what it should look like on the 48,000, the 24,000, and the 8,000 sampling rates as well. For your report, you should describe what you've seen here in this video, explain what's going on when the different downsampling techniques are applied. The report asks you to write your C code, but I don't think you're going to need to do that, given that you've already seen my C code here today. Nonetheless, hopefully you can show me some understanding of what's gone on here today, describe what you've seen and why it's going on. Wish you the best of luck, and I'll see you in lab 2.